Leah here from LeahForSci.com, and in this video we're going to look at charged and heterocyclic aromatic compounds. In order for a molecule to be aromatic, it has to be cyclic, planar, conjugated, and follow Huckel's rule. But that doesn't mean that the entire ring has to be composed of carbon atoms. We're used to seeing molecules like benzene, which is very simple. 6 carbon atoms in a ring, 3 pi bonds, nothing else, good to go. When you see something different, such as a negative or positive charge, or even another atom in the ring, you want to evaluate the criteria regardless of what else is going on. You still want to evaluate by this checklist, recognizing what to expect with charges and heterocycles. Before we continue, make sure you review the previous videos where we discussed the criteria for aromaticity. You can find this on my website, leahforsci.com/aromaticity. Let's start with the aromatic cation, or simply the cation. A cation tells us that there's a positive charge. For example, if we have a carbocation, we have a carbon atom with bonds to 3 other atoms, which we'll show as green lines, and then an empty p orbital that sits above and below the carbon atom. A cation is sp2 hybridized. There's nothing in there, there are no electrons. Instead, that p orbital is open and willing to accept another electron pair, for example, to form a pi bond. When you studied resonance, you saw that pi bonds or electron pairs are very happy to move over towards a positive carbon atom, which moves the carbocation to the carbon that lost the pi bond, but creates for a resonating system. We've already seen this molecule with a pi bond and a carbocation, so let's break it down. How do we know if it's aromatic? The molecule is cyclic. I can trace a circle around the entire compound. It's planar because every carbon is sp2 hybridized. The carbons holding the pi bond, as well as the carbocation. We know that the pi bond can resonate into that empty p orbital, either towards the left or towards the right, making this a fully conjugated system, and then we'll use the shortcut for Huckel's rule. We have a total of 1 pi bond, which is odd. An odd number of pi bonds follows Huckel's rule, making this molecule aromatic. Yes, it's tiny. Yes, it's under a lot of strain, but it's still aromatic. We've seen that cyclopentadiene is non-aromatic because of an sp3 carbon atom. But what if we change it to the cyclopentadienyl cation, meaning a positive charge on the carbon that doesn't have a pi bond? The molecule is cyclic. I can trace a circle from start to finish. The molecule is planar because every carbon atom in this ring is sp2 hybridized, the carbons holding a pi bond and the carbon holding the carbocation. The molecule is conjugated because the pi bonds can resonate in the direction of the carbocation clockwise or counterclockwise. But does it follow Huckel's rule? Let's see. We have a total of 4 pi electrons or 2 pi bonds. That means we have an even number of pi bonds, and even does not follow Huckel's rule. It's anti-Team Huckel, making it anti-aromatic. Aromatic anions are evaluated the same way, with one difference. An means without, but in this case, it means without or negative because we're dealing with a negative charge. If we have a system with a pi bond next to a carbanion, the negative electrons can resonate towards the pi bond, kicking those electrons, which gives me a resonance structure that now has a pi bond in the middle and a lone electron pair on the left, definitely capable of resonance. In order for these electrons to resonate, the carbon has to hybridize to sp2, putting the lone electrons into a p orbital so that it can participate in the resonance. And this is something to keep in mind when evaluating the aromatic anions. We'll take our same cyclopentadiene, but this time we'll give it a lone pair rather than a carbocation on this carbon atom, which means it also has a negative charge. Let's evaluate. We already know that it's cyclic. Because these electrons can resonate into the pi system, they have to sit on an sp2 hybridized carbon atom, which means all of the carbons are sp2 and the molecule is planar. Because the anion can resonate into the ring, that makes it a conjugated system, but does it follow Huckel's rule? We have 2 pi bonds, which means an even number, but remember that for Huckel's rule, we're not looking at the number of pi bonds as much as the electrons that are resonating, or for the shortcut, the electron pairs that are capable of resonance. We have a total of 6 electrons or 3 electron pairs, which means we have an odd number, and an odd number means it follows Huckel's rule. That makes the cyclopentadienyl anion an aromatic anion. Let's compare it to this 6-carbon anion. The molecule is cyclic because I can trace a path around the ring. I do notice the anion, which means if my mind jumps to Huckel's rule, I'm thinking 6 electrons, 3 electron pairs, odd number, should be aromatic. But what else do we have going on? Yes, the negative electrons can resonate into the ring, making part of the system conjugated. But don't forget, we also have this carbon over here. This carbon is not able to participate in resonance because it doesn't have a charge and it doesn't have a pi bond. It's an sp3 hybridized carbon, meaning it's tetrahedral or 3-dimensional. That means the molecule is not going to be planar and the entire ring is not conjugated because we can't resonate onto sp3. This sp3 carbon is uninterested in aromaticity, is a non-baseball fan, making this a non-aromatic compound. Let's move on to heterocyclic aromatic compounds, remembering that hetero means different, and a heterocyclic compound is a molecule that has something different in the ring, meaning other than carbon atoms. For example, this molecule right here often comes up on exams. Is pyrrole an aromatic compound or not? More importantly, how do we evaluate when we have something like a nitrogen atom in the ring? Here's the trick to remember with heterocyclic compounds. Heterocycles, just like any molecule, wants to be aromatic. This is something that you'll hear me say over and over and over. It applies to organic chemistry, just like it applies to your entire life. Happy is going to give you something that is stable, is going to be unreactive. If something is unhappy, it is unstable, and that makes it reactive. We said that aromatic compounds are very stable, so when possible, everything wants to be aromatic if it can. A heterocyclic atom, if it has the ability, will try to contribute to aromaticity. But in order to be aromatic, it has to resonate. So here's the question to ask. Does the atom participate in resonance already? All you need is one participation. An atom can't join resonance with 2 separate electron pairs at the same time. It's 1 pi bond or 1 lone pair. That's it. If the atom is already participating with a pi bond, you don't add the electrons in. If the atom is not participating, you use the lone pair. Again, if the atom has a pi bond, you don't use its electron pair. If it has no pi bond, you use its electron pair. If it has 2 electron pairs, you only need 1, because 1 is enough to participate. Let's see how this applies to pyrrole. Is the molecule cyclic? Why, yes, it is. I can draw a circle around the ring, including the nitrogen atom. Is the molecule planar? Let's see. The carbons have pi bonds, they look sp2 hybridized. The nitrogen atom appears to be sp3 hybridized. It's got 3 bonds, 1 lone pair, which would sit in a hybridized orbital, except for the rule you should remember from resonance, and I cover this in the series link below. If the atom has the ability to resonate, then it will hybridize so that it can resonate. That means even though nitrogen appears to be sp3, the nitrogen is sp2 hybridized so that it can participate in resonance, which means the molecule is planar, everything's resonating, and it means the molecule is conjugated. But do you notice how we had to ask the question. Nitrogen was not participating in resonance because there's no visible pi bond, and so we had to take its lone electron pair to contribute to the aromatic system, so we have to use its electrons for resonance. Let's attempt a side view of this molecule, and you can build this with your model kit. We'll make these two as the rear carbons in black. We'll make these two the forward carbons in purple. We know that for resonance, we have the p orbital sitting above and below, so we'll draw above and below in two different colors. And then we have a nitrogen atom right over here. If nitrogen is sp2 hybridized, that means it's going to have 120-degree bond angles between nitrogen and the things it's bound to. That puts hydrogen perpendicular to this system, facing completely out of the way. But then we have that p orbital where the electrons would sit. We've seen that we have a pi bond here and here, like this. But now nitrogen can take those electrons, resonate towards the pi bond, giving me that conjugated system. Let's verify with Huckel's rule. How many electron pairs do we have? 2 pi bonds and 1 lone pair gives me a total of 3 electron pairs, an odd number of electron pairs, which means it supports Team Huckel and it's aromatic. Another common molecule you'll see is pyridine. Pyridine, like pyrrole, is a heterocyclic compound that appears to be aromatic. Let's take a look. Is it cyclic? Yes, it is. Is it planar? I see pi bonds everywhere, all sp2 hybridized. Yes, it is. Is it conjugated? It looks very much like benzene. In fact, if I pretend the nitrogen isn't there, it's exactly benzene, which means it is conjugated. But what about Huckel's rule? I have 3 pi bonds and 1 lone pair, giving me a total of 4 electron pairs, or an even number, which wants to tell me that the molecule is anti-aromatic. We have to go back to the rule. Nitrogen wants to participate in aromaticity. In pyrrole, the only way to play was to bring its own electrons. BYOE, bring your own electrons. But in pyridine, we don't need that because nitrogen already has a pi bond. It's already part of the resonating system. That means these electrons don't get to play along, therefore they're not counted. And so we have 1, 2, 3, an odd number of electron pairs, supports Team Huckel, making pyridine aromatic. Let's take a look at a side view so you understand why these electrons can't even try to participate. We'll show these 3 carbons in black, and the forward carbons in purple, and nitrogen on the side. We'll show the upper part of the p orbital in light blue, including on nitrogen, and the lower part in gray. And look what happens. We have a pi bond here, we have a pi bond here, and we have a pi bond here. That is a clearly resonating system, but what about the lone pair? If nitrogen is sp2 hybridized, then imagine that this lone pair is really a bond to itself in an orbital that sits at 120 degrees perpendicular to the molecule. Even if these electrons wanted to participate, they're sitting at 90 degrees. They have no way of interacting with the pi system. That is why we don't count them, and that is why they're not used. For even more practice on heterocyclic aromatic compounds, aromatic ions, and more, first, give this video a thumbs up, then visit my website, leah4sci.com/aromaticity, where you'll find the aromatic practice quiz as well as the common aromatic compounds cheat sheet. The link again is leah4sci.com/aromaticity.